Hello everyone, my name is Claude Henny, researcher at the Network Security Group at ETH Zurich, and today it's my great pleasure to introduce you to Mondrian, the comprehensive interdomain network zoning architecture. This work was a close collaboration with Jong-Hung Kwon and Adrian Perrig from the ETH Zurich Network Security Group, as well as Patrick Bamert from Zürcher Kantonalbank. I'd like to start by giving a short introduction to network zoning, explaining the concept on a high level, before showing how it is implemented on a more technical level. Network zoning is the grouping of information assets into segments that exhibit similar security requirements or similar functionality. For example, one might want to separate sensitive customer data from less critical data, or with the rise of connected devices, it makes sense to group IoT devices into their own segment. Such groups are called network zones. These zones have dedicated entry points where traffic is filtered to make sure it complies with security policies. On an abstract level, these policies are often realized with a zone transition matrix, describing which zone transitions are allowed and which are not. Now I'd like to proceed with a small case study, showing how network zoning is commonly implemented today. In this figure, you see an example of an enterprise network consisting of multiple branch sites with multiple zones at each site. These zones are typically implemented via a layer 2 virtualization technology, such as VLAN, where a VLAN ID is mapped to a certain IP subnet. These zones are structured hierarchically, meaning that traffic destined for certain zones needs to pass other zones first. One special zone to mention here is the transit zone that acts like a patch panel, interconnecting the other zones. What is also apparent is the heavy use of security middle boxes, such as firewalls, IDS, and IPS systems. An interesting thing to note is that enterprise networks oftentimes operate the same logical zones in multiple branch sites. Here, for example, the control zones. For interconnecting sites, mainly two technologies are used, leased lines and site-to-site VPNs. With this, we can now analyze what the challenges are in such a setting. The first problem is the loss of zoning information. Security information about network packets is lost once the packets cross the perimeter of a branch site. This requires the remote branch site to re-establish that information using firewalls or other security middle boxes. These are costly checks for packets that have been sent by a trusted peer. Even worse, because of the hierarchical zone structure, packets are usually checked multiple times before they reach their destination, even if the packet stays within the same logical zone. Furthermore, there is a multitude of virtualization technologies available on the market. Different vendors support different protocols, and not all locations have access to all vendors. This circumstance leads to heterogeneous enterprise networks with protocols that are incompatible with each other. Achieving seamless communication in these settings is challenging. The last point I'd like to make is that administration of network zones is a tedious and error-prone task. This is true for a single branch site, but even more so if you think about the interdomain setting. Simply adding a new zone to a site might require thorough review of policies followed by updates to all involved firewalls, locally and at branch sites. Achieving consistency on this large number of management points is time-consuming and expensive. So in summary, we identified three main challenges of current network zoning architectures that we want to solve. The loss of zone information when sending between branch sites that cannot seamlessly communicate with each other because of incompatible protocols, and poor management scalability, caused by a multitude of systems that need to be touched for every update to the network. A new architecture should therefore solve these issues while maintaining a high level of security and deployability. Before showing the Mondrian architecture as a whole, I'd like to highlight one concept that enabled us to solve the aforementioned challenges. It's the concept of what we call the interdomain transit zone. If you recall, the transit zone is a special zone not containing any end hosts, Its purpose is to interconnect local network zones. It's a point where zone transitions are made and checked for their validity. With Mondrian, we scale this concept to interdomain networks. The interdomain transit zone spans across a wide area network, for example the Internet, connecting branch sites of an enterprise. Branch site local zones are attached directly to this transit zone, flattening the formerly hierarchical network structure. This in turn means that fewer security checks are required, as all zone transitions can be checked at the border of the interdomain transit zone. Inside this transit zone, the Mondrian protocol is used. This protocol can transport zone information across the interdomain transit zone, allowing remote destinations to easily verify zone transitions. This solves the first issue we identified in today's architectures. Additionally, the Mondrian protocol is independent of the internal protocols used at each site, solving the incompatibility issues. With knowledge about this important building block, I'd now like to explain how the Mondrian architecture works. In this figure, you see an example deployment of Mondrian. Multiple branch sites containing multiple zones each are connected via the interdomain transit zone. This transit zone is spanned by dedicated security gateways deployed at each site, to which all local zones are connected. These gateways are called transition points, or TP for short. The main task of TPs is twofold. First, they ensure that traffic doesn't violate the zone transition policy. For that, TPs check all zone transitions against the policy they receive from a logically centralized controller. This controller has the full view over the network and makes sure that all sites operate with the latest security policy. For zone transitions that cross the interdomain transit zone, the second job of TPs is to attach cryptographically secured zone information to each packet, then encrypting the packet before sending it over the internet. This way, we make sure that no sensitive information, such as internal addresses, are leaked. The receiving TP can then verify the zone information, decrypt the packet, and if all checks succeed, forward it into the local network. The logically centralized controller is the single interface with which network operators manage their network. It offers a comprehensive interface for manipulating sites, zones, and transition policies. The controller then takes care of distributing these policies to the TPs, which enforce the policies at the individual premises. Supporting zone transition policies with application granularity offers great flexibility for operators to cover a vast number of use cases. This centralized interface simplifies today's complex setups with potentially many systems that need to be updated for every change to the network. As a result, Mondrian is less susceptible to configuration errors and makes policy reviews less time-consuming. Combined, these properties greatly improve management scalability. Because Mondrian encrypts and authenticates packets, a key management scheme that scales to big enterprise networks is required. One possibility is to do the tunneling with site-to-site granularity. This is how IPsec VPNs work. In such a system, the number of keys scales with the number of branch sites, which is not a problem. However, one design goal was to achieve tunneling with zone granularity rather than site granularity, meaning that different zones should use a different key. This is not possible with this approach. Another approach is to use keys for each pair of zones. This would, however, expand key state too much, as in large networks the number of zone pairs becomes very big. Therefore, for Mondrian, we designed the concept of site-to-zone tunneling, where source and destination TPs first establish a shared symmetric TP-to-TP key, from which they can then derive a second site-to-zone key. Since this derivation can be performed efficiently, it is not required to store these site-to-zone keys. This approach ensures that different keys are used for different zones, while the required state scales with the number of branch sites rather than the number of zones. We implemented Mondrian as an open source project, building on top of the Cyan Internet architecture. The transition points are built in a modular way, with different modules handling the zone authorization and zone authentication. Thanks to the modular design of the TP, other modules can be added easily if needed. Modules are connected via the core module, which reads packets from the interfaces before handing them off to the other modules. The controller has been implemented as an HTTPS web server. We then evaluated the performance of the individual modules. In this graph, we plotted the latency inflation caused by a single policy check on a network packet. With only 300 to 400 nanoseconds, the added latency is negligible. There might be an authorization abort due to three possible reasons. Either the source zone is unknown, the destination zone is unknown, or the transition is forbidden. In such a case, the transition is rejected after as little as 100 nanoseconds. Furthermore, we were interested in the performance of the key derivation system. This table shows the average key derivation times for the TP to TP level and zone level keys, which are around 190 nanoseconds and 100 nanoseconds respectively. Therefore, the full derivation chain is completed in less than 300 nanoseconds. It's noteworthy that the added latency is mostly unaffected by the number of branch sites in the network. This table shows the additional processing time for packet authentication with combined encryption on the sender side and decryption on the receiver side. As expected, the main factor influencing the processing time is the size of the packet, with encryption of a full-size packet taking less than 1.6 microseconds and decryption less than 1 microsecond. In summary, the process of encryption and decryption requires approximately 1.5 to 2.5 microseconds, depending on the size of the packet. Lastly, we investigated the actual forwarding performance for various sizes of packets, including a representative mixture of Internet traffic, IMIX. The baseline is the forwarding performance without Mondrian operations. The other bars represent the performance for the intradomain use case with authorization only and interdomain use case with added authentication respectively. We observe almost no degradation for the first case, whereas the latter case suffers from a performance hit, especially for small packet sizes. This is expected as a degradation not only is caused by the processing overhead for authentication, but also the transmission delay of the encoded zone information. To summarize, Mondrian provides increased scalability for network zoning. The reduction of management points and the capability to join networks with different underlying protocols, combined with a central management interface, greatly simplifies network orchestration. Giving operators the tools to create network zones with application granularity offers great flexibility and enables various interesting deployment models. At the same time, with authenticated zone transitions and encrypted interdomain traffic, Mondrian offers high security. Lastly, efficient cryptography and low operational costs make Mondrian an interesting candidate for enterprise networks. For more information regarding protocol descriptions, implementation details, and practical considerations, we invite you to read the full paper. With this, I conclude my talk, and now I'm happy to take your questions.